All right, so we're going to continue talking about essentially the SVD. And as I said, it's kind of magical in many ways because of all the things you can do with it. And we're going to shift gears a little bit to talk about what's called independent component analysis. Okay? So let me write that up here. You got to be careful where you stop that one. Everybody awake yet? Okay. All right. ICA for short. So you see, we have SVD, we have PCA, we have POD. Now we're just going to add ICA. And here's my claim. You already know this one. You know this one well because you do it all the time. Let me give you the classic example. It's called the cocktail party problem. All right. So here is the basic concept. We'll illustrate it through a little cartoon. It's not, cocktail party sounds fancy. Kegger. We're at a kegger, and there's two groups of people talking. All right? And here's the idea. Here's the experimental setup. So you have conversation 1, conversation 2. People are conversing. Suppose I place 2 microphones in the room. Okay? And so here's the deal. 2 conversations happening. I can record them here and here. So at microphone 1 and microphone 2. And what I have here is 2 signals being produced, 2 acoustic signals. Let's call them S1 in time and S2 in time. However, when I record them, right, I get a mixing of these 2 signals. Right here at these microphones, I have a little bit of S1 and a little bit of S2. Am I flashing back there on the TV? There we go. Okay, now that stopped. All right. Okay, does that make sense? Now here's the mathematical problem you want to do. Can I, with these 2 measurements, actually separate back out these 2 signals? Okay, that's the mathematical idea. Now we do this all the time, right? We can be in a conversation, you hear a word, and you can almost instantly train your ear. We do this, right? You can kind of almost eavesdrop of what's being said over here. Even though you have all this signal over here, you can actually extract that signal out, provided it's not too loud and everybody's speaking sufficiently high volume, right? So this is the idea of what we want to do. Now, from a mathematical point of view, then, you say I have 2 signals, and let's take recordings at microphone 1. Let's call it X1 and X2. And I take these recordings, and here's the idea. My recordings at the microphone 1 and 2 come down to be something like this. I have signal S1, I have signal S2, and I record some linear combination of these 2 signals at microphone 1 and at microphone 2. So what I have is these guys, and what I want is S1 and S2. The parameters A, IJ, are the mixing coefficients. Okay? And what I'd like to determine is how to handle that. A couple of things to note right away is part of the deal here is you don't know what these A's are, right? So let's do a little count. How many things do I not know? I mean, not me personally, because that's like infinity. But here in this problem, you don't know this, you don't know that, you don't know this, you don't know that, you don't know this, you don't know 6 things. 6 things, 6 unknowns, and 2 constraints, right? So this is kind of a bad deal for you, because typically we think about, oh, well, you can't solve a problem like that, because you have too many unknowns and not enough information to actually solve this, okay? So we're going to talk about techniques to actually figure out how to not get these, but to approximate these. Okay? All right. Because if you knew the A's, then getting the original signals is trivial, right? This is really just something like this. And if you want your signals out, you have something like this. And if you knew the A matrix, that's easy, but you don't know the A matrix. And how would you determine the A matrix, by the way? So the A matrix depends a lot upon the actual placement of the microphones as I move them around the room. Depends upon what the room shape looks like. And we're ignoring a lot of effects, like, for instance, acoustic waves bouncing off the wall and so forth. Okay? But you can see if you could find an algorithm that does this, you could place microphones in the room and tune in to different conversations that are going on. Now, by the way, where does this apply beyond just sort of cocktail party conversations? Well, we've already talked about many examples, but here's some that you would see that are easy ways to think about conceiving where this would be important. Radar detection. If you looked at all the radar detection stuff we did, we are saying we send out a signal, it bounces off a plane, and it comes back. Well, what happens if we send our signal out and there are multiple aircraft out there? One. Okay? So stuff's bouncing off more than one target, let's say. And part of the deal is we would like to actually figure out how to pick out different targets. We want our radar to actually pick out all the targets in the air. And one of the key things that's going to happen here when we try to actually apply this method and determine those A's is that we're going to assume something about these signals. In particular, we're going to assume that the signals produced from different targets, like the airplanes, or the signals produced from different conversations are going to be statistically independent. Okay? If they are statistically dependent, we're kind of in trouble. But as long as we make that assumption that, look, this conversation, and the pitches and the voices and what they're talking about somehow is completely different than here, then we have this idea of statistical independence, and that's going to be the main thing that's going to allow us to basically get out these mixing coefficients. Another application where independent component analysis is really big, not eggs, EEG. So EEG is basically you put a bunch of, electrodes, things like that on the scalp, which measures brain activity, essentially. So part of what you'd like to do is, if I have enough of these on the brain, I measure some kind of overall activity. But really what I'd like to do is separate out the different signals that are actually going around in my brain. Okay? So different parts of the brain sending different streams of information. If you assume that these different parts of the brain are actually assuming statistically independent thoughts, I don't know, whatever, things. Probably not thoughts all the time. But things going around in my brain, how do I pick out what is there? Okay? And the final one, which I love, so this is really much more practical. In Terminator, the new one, so you saw that in Terminator, they found this hidden signal upon all the signals that were sending out to control all of Skynet, and they said there was a hidden signal on top of it. So somehow someone in this class in the future finds this. It could be Matt. Maybe Matt's in the future, and he found this signal, and he basically used the method SVD, and he found this signal, and that's how they found out how to shut off some Terminators. Anyway, you see how important it is? I know, Maria. Maybe you're not understanding how important that is, because you could turn off a Terminator with your skills that you learned today in class. So everybody pay attention. You're needed in the future. All right, any questions on it? You see what happened here? We're just taking signals. We're trying to separate them. All right. And we need a mathematical technique to do it. All right, so that's the concept. So let's try putting this thing in some kind of framework mathematically that allows us to compute this. And then we're going to focus on a very specific example of how to do this, which is going to be an image analysis problem. And I'll present that a little bit later. Okay, here's a more formal framework for this, okay? All right. Here it is. Given n distinct n distinct linear combinations of n signals. Okay. Determine the original n images. Okay. So that's the statement. I have the idea is that somehow I have n signals all being mixed together. I have n measurements of these things. So somehow they are n linear combinations, right? So wherever I place measurements, devices, things like this in my system, I read off n things. And then with those n measurements, can I, in fact, infer the original n images that are actually mixing? Okay? Does that make sense? So in a more general setting than just this 2x2 system, what I really have is I have some x of j, which is going to be my measurement, is going to be some kind of linear combination like this. So I have some jth measurement, and it's a linear combination of my signal S1, S2, S3, S4, all the way to S of n. Okay? Or expressed in matrix form, where I calculate all of these matrices, what I have then is this. The only thing I know about this equation is x. That's what I measure. And these guys over here, we don't know. And I want to find some mathematically self-consistent way to approximate what these are. Okay? That's going to be the best. And by the way, I want to do this in such a way that I make the minimum number of assumptions that I can. Okay? So in other words, you'd like to make it as general as possible. How do I reconstruct the original signals based upon my measurements of the mixed signals with as few assumptions as possible on how they mix? Okay? Because if you make it too restrictive, most likely is you have an experiment that you can't actually do, right? I mean, so you have to try to make it as general as possible to make this work. All right. This is called independent component analysis. That is what you want to do. You want to pull out the independent components that are sitting inside of this thing from your measurements. So we talk about sometimes images, sometimes signals, but you can actually see that this has a much broader impact, which is you give me data sets of measurements. What's to say that there actually isn't all kinds of processes that are actually coming into your measurement that leave a big signature, but may be completely statistically independent of what you actually are after, right? So you get some measurements, and it's polluted with some other measurements. It's not necessarily a bad thing, but you have to figure out how to withdraw those things out of this thing. Okay? That's the purpose of this. So for instance, if you're in atmospheric science, maybe you're getting some measurements, and you're interested in one kind of behavior out of the system. Can I quantify a certain thing? But when you do the measurements, you're actually getting a bunch of other effects. They may be statistically independent, and you'd like to just remove them, so you just isolate what you want. All right. Let's do this in a graphical way. Let's think about it this way. One of the things we had talked about with principal components, so we want to talk about PCA, and how does it relate to ICA, besides just the first letter change. Okay? They both have this idea of component analysis, One of them is principal, one of them is independent. What's the relationship? So let me draw a series of figures for you to graphically illustrate how we want to think about this. Suppose I take some measurements. This, in fact, could be something like from camera 1 that we did on the homework. And I just plot position data that I get. And maybe it looks something like this. All right. Do you guys like that sound? Okay. All right. A little bit annoying. But it's all right. But suppose I got something like this. All right. I took some measurements. And what do we do? Well, you know what we do? We take this thing. We subtract off the mean. So we put ourselves right in the middle here somewhere. And then we do this SVD. And we say, tell me which directions are essentially the most important in this system. And when we do that, what you would find for something like this is there is a direction. Probably. It's the whatever. You know, we've talked about this as being what's going to pull out for you is the semi-major axis of an ellipse that sits there. If it's 2 degrees of freedom, the SVD pulls out major axes. Okay? And it pulls out the biggest one first, second biggest one second, third, and so forth, and it pulls them out in orthogonal directions. So for instance, if you were to do an SVD on that data set, which you are going to do for your homework, you'd get something like that. And that tells you, there's my principal component, and has some value sigma 1. That kind of gives the strength of that component. And then for this data, you could even go to sigma 2, which would be orthogonal to it. So this is where we need red pens. But fine, can you all see that? There we go. There's your sigma 2. It does this principal component decomposition. Tells you that most of my energy is in sigma 1. I got a little bit in sigma 2. And this is a simple 2-dimensional problem. But you can imagine you can have higher dimensions. And it would just project everything down to some appropriate bases. Okay, good? That's what we do. That's SVD and PCA and POD in a nutshell, that picture. Anna? No? Do you like that picture? she was giving me like, So I was like, okay. All right, well, anyway, maybe you don't like my drawing, so it's okay. I'll try to improve. Now, let me give you a second data set, and let's talk about doing the same kind of idea. But I take some measurements, and here's what I get. Okay, I'm going to make noise. Just bear with me. Yeah. Okay, suppose there's my measurements. Some other experiment. And this is what I get. I project all this stuff down. Here's what I plot. Okay, now first of all, part of what we're training our computer to do is to do everything automatically for us. So sometimes you might just say, hey, I got this thing figured out. All I got to do is take the data, put it in, say, SVD, and just look at sigma 1, sigma 2. But there's a value in saying, okay, now this makes sense. Let me project my data. Let me put my principal components on this and so forth. Because if you were to just blindly apply your SVD right now to this thing here, just put the matrix in, SVD, pop out your orthogonal modes, pop out your sigma 1 direction, which is your principal axis, it would probably look something like that. And you could ask yourself, is that a good representation of the data? And I hope you would say the answer is no. Actually, there's nothing along that principal component at all. You somehow got data lined up here. You got data lined up here. You got nothing in this direction. And so what it's somehow telling you is that you've missed something kind of important about this. This is misanalyzation a word? I don't know if it is, but that's what you've done. It is now. You've misanalyzed that if that's what you pull out. That's a straightforward PCA application of that data set. All right, so what's the problem? The problem seems to be that, in fact, there's really sort of two principal directions. There is a data set lined up here in which you could extract out a principal mode here and a principal mode there, sigma 1, sigma 2. There's also a data set along here which you could extract out, let's call it sigma 1 bar, sigma 2 bar. This is an illustration of the independent component analysis. What you've got here is two data sets that seem to be independent of each other. clearly, stuff's happening here, stuff's happening here, two different phenomena. And in some sense, what you want to do is do an SVD of this data and SVD of this data. You want to separate them. Okay? This is what it might look like if you looked, for instance, at the data that would be generated at microphone 1 and microphone 2. The conversation's happening here, and the conversation's happening here. Maybe you have, you know the one dude, really loud guy, he's always at a party. He usually goes outside and sits on the porch, and everybody in the neighborhood can hear him. Well, anyway, I live close to here, and I know this one guy. There's always one of them at the party. And he's always hot, so he always goes outside, and he wakes everybody. He's always got the beer. And his voice is super, super loud. So it's hard to see if anybody else come in. But, you know, there's also the girl who has the higher pitched voice that also is outside, and you can hear her really well. Like I said, I live close to campus, so I know these things. So let's make it go here. All right. So for instance, if you were to record these things, and they're dominating the conversation, and it's about 1 in the morning, and they're just super loud, out of control, because this thing controls their volume right here. And after about 10 of them, their volumes are just way up. Okay, so they're talking really loud. They're picking them up here. But, you know, ultimately, these are two very different voices, two different cadences, two different measurements that you take here. And when you look at the data from X1 and X2 and start projecting out this data, it's a linear combination, but you might get something that looks like this. Here's the one person talking. Here's the other person talking. To decompose them is to mix their sort of voices in some sense. So what you want to do is separate out the signals. And once you separate out the signals, then this and this make sense. Okay? Everybody understand that graphic? It's really important to understand that's the key thing right there. So whenever you have data, and if you can, in fact, project it to some low-dimensional thing like this, you first want to take a look at that data. Does it make sense for you to just simply do an SVD straight up on the data? Because, in fact, if you did, like I said, you'd be getting a vector like that, which is sigma 1, which is actually doesn't really tell you what's going on in that data set. They would be like somehow representing the S as a function of time in volume or pitch or something like that. You'd make up some variables that you're trying to pick out of that signal.
So the first step we have to do is somehow get from our X's to...
Yeah, so, well, okay. So, actually, no, you don't know the S's. You just have some measurements. And the idea here is I've only given you one variable, but you might be measuring from microphone 1, let's say, volume versus frequency, for instance. You could take two quantities. That's why, so I made it two-dimensional, let's say. So for microphone 1, let's suppose you measure two things from conversation 1, two things from conversation 2. So you don't, I mean, you don't have to measure one quantity, but I'm just saying if you do two. That's the graphical depiction. This really doesn't make that much sense into there, but I'm stretching it. It's just a cartoon. So you shouldn't take it too seriously. Just like my stick people over there. Not serious. Yeah, Richard.
In there before ICA or MATLAB just goes and freaks out and runs away?
Good question. I don't know. Okay. I can, you know, the more recordings you have, the more likely you are. So there's a point at which you over-determine the system, right? And so now you're checking for consistency. But if you were to keep taking measurements there, you could then, for instance, in that simple example, if you just did this, you have here 2 constraints, 6 unknowns. You can imagine I put 4 more mics on. That's 4 more constraints. Then I could potentially pin down the A's. Well, actually, I'm adding more A values, right, too. So potentially you could, however, start refining it more and more as you get further down. What you'd really want to do instead is get more information at each microphone. Right, so the A1 and A2, A1N1 and A12 stay the same, but you just keep adding more data to nail down those parameters. Okay, let me finish off with one last cartoon here. Normally, that's a good, okay. that's kind of a normal distributions are bad. I was going to say normally you don't. Well, the last thing you need right now is Gaussian variables. Gaussian distributed variables kill ICA. Here's why. Suppose I have a Gaussian distributed variable. Ready? More noise. So tell me, suppose I have really two independent signals in there, and I get them to be Gaussian distributed. Which way is sigma 1, which way is sigma 2? Right? You've got this inability to extract out principal components at this point. Okay? Is that it? I can rotate that any number of degrees I want, and it's still kind of look the same. So what ends up happening if you have Gaussian distributed random variables, PCA breaks down. ICA breaks down. So one of the assumptions we're going to make here is that we're not going to have Gaussian distributed variables. Okay? And by the way, we're going to use this extensively to do our image analysis. Okay. Questions on anything so far? Everybody good so far? You guys want to come over and hang out at my house? No? Okay. Not yet. All right. I haven't made a convincing argument. Okay. Now we're going to do a very specific example. The specific example, it's going to be awesome. I would assign it as homework, but you have these, these homeworks now. You got a report to do. So, but we're going to work this out completely in class, and it's going to be, I think, a really nice problem. Here it is. By the way, we're all familiar with this as well. And what's amazing is how well we actually handle this. Here's me. There is a beautiful piece of art. I don't know, some people, maybe a mountain. Oh, that's art. Okay, there we are. And I'm looking at this beautiful piece of art. Now, it turns out this piece of art was done by someone very famous. So what they tend to do then is put it behind glass. Okay, that's glass, because you can see through it, right? All right. Oh, you know what you do in your cartoon? Isn't it like supposed to show you that it's glass? Okay, glass in front of this thing. Interestingly enough, first time I ever saw the Rosetta Stone in the British Museum, you could. I was very hard. I wanted to give elbows to these people who are touching the Rosetta Stone. They don't know what it is. They're just getting their grubby hands all over it. I was like, I couldn't believe it. Just because it's a rock, they think they can touch this thing. Anyway, they now have it behind glass. I'm so happy. But here's the thing. I'm looking at this image, and there's a window back over here somewhere. So it's some light source over here. So the reflection, so when I look at this image, the light not only lights up the piece of art, but the glass itself reflects a good portion of actually the light that comes. So in other words, before it even gets to the art back there, it's reflected off the glass. All right? So just take a look, in fact, out the window on any day. If you can often see, you see outside and you see your reflection sometimes, or you see the reflection of your room right there on the glass. Okay? So that's the problem we have. So now when we take this picture, if I took a picture, here's my iPhone, and I take a picture of this. I don't just get that image. I get the image plus maybe there's some kid over here touching the Rosetta Stone I want to kill, and he's in the picture now. Okay? And I have to edit that out because it just makes me angry every time, and it's not good for my health. Okay? So this is you see how important this problem is? All right, good. I just want to set the, Terminator, we're working on solving Terminator problems plus this. Look at all the skills you pick up in this class. At the end, we're going to make a big list of all the things you can do, like destroy Terminators, remove kids touching Rosetta Stones. It's going to be awesome. That's exactly it. You could work for CSI after this, too. I'm going to add that to the list because the murderer is right over here. All right, or the art theft. So let's go classy. Okay. All right, so there we go. I have an image. I have the reflected image. And basically, I want to extract one from the other. Now, interestingly enough, we are quite adept at doing this on our own. You can look through the window. You don't even see the reflection that's clearly there. Like, we just train ourselves to look right through it. But if we want, we can actually, I'll focus in on the reflection. We can pick out images amazingly well. Okay? Try that sometime. Take a reflection. Focus just on the reflection. You can actually make out them almost like it's a mirror. Not quite as good, but you have an amazing ability to extract out that image that's the reflection. Then you can also just say, I don't want to see that. I want to just look through to the picture behind it. And it's amazing how you almost don't see the reflection. That's what we want to do. Ultimately, there's a kind of a principle here, which is some people are trying to teach machines how to do virtual seeing, right? And how do you extract these images? Because we can do it without any problem, it seems. And that's going to be the concept. So let me turn on the overhead camera here. Let's see. Is that overhead camera? Oh, I got to pull this down, right? So that you guys can see this. Will, we're going to get fancy here.
Okay.
All right. Are you ready? You're not ready for fancy at oh, it's past 9 now. All right. All right, I just turned the display on, yeah? All right. So I didn't have to go very far. I went right into my office to get you 2 examples of pictures. Okay, so let's do this. Okay. And do I need to do anything else? Project local, is that right?
Yeah.
All right.
Then document.
Oh, document camera. There we go. There we go. Okay. Let's see if it switches over. Perfect. Okay. Do you want to switch over the, turn off the lights in front here? Yeah.
This is the tricky part.
Oh, shoot. Okay. What do you think? What was better? This? Do the other one?
Lights on or off?
Let's do lights on real quick. All right. Is that it? Yeah? Is that same? It's like going to the eye appointment. This or this? And you sit there and answer that question for 10 minutes, and they say, okay, here you go, done. It's like, I don't know what you did, but fine, all right. All right, here is a picture, an image. If you've paid attention some of you have been to my office, many of you have not, but there's a picture up on my wall. Do you know this one? Have you seen it? Did you even look at my wall? Am I just wasting my time with art on you guys? You guys have seen it because you've been in there so many times. Edwin, really? Come on. You don't have a picture? I have this picture on my wall. Here is, in fact, a great classic mythological scene, the Judgment of Paris. Here's Paris right there, and he's got the apple, the golden apple, for the fairest. Oh, well, nothing gets a goddess going than to know she's the fairest. So what we have here is a contest. This was dropped off at a wedding party of Peleus and Thetis because Discord didn't get invited. She was a little ticked off, so she throws this golden apple on the table and says, just for the fairest. And of course, these 3 lovely ladies over here all believe they are the fairest. We have Hera, and we have Athena, and we have, of course, Venus. And then they have a contest. They decide, uh-oh, nobody wants to decide this, including Zeus. He's like, wants to stay out of this because this is really problematic. He's going like, let's have some dude decide this. There's a guy, Paris, let's go over there, and here's Hermes, and they say, okay, you are going to decide who the fairest is, right? So there's the golden apple to give. And so they each promise him something. Juno promises him, or Hera, promises him he will be the greatest ruler of the land, rule over vast empires. Athena promises him to be the greatest warrior of all time. Sort of kind of a promise that was made to Achilles, really, but, you know, he could have taken it instead. And then, of course, and then Venus comes along and promises the most beautiful woman in the world. Uh-oh. Okay, well, here. So there you go. That is the scenario. And of course, he picks up Venus. This is the tragedy of the Trojan War, because the woman that comes out of this deal is Helen of Troy. So he goes and steals her, brings her over to Troy, and then, of course, a big war. So this is by this guy, John Flaxman. So he does this painting. So now what I did is I took a picture of this. Now what you can see here, that's my office window. There's a reflection of it. It doesn't show up quite as well here, but you can actually look in the reflected image. If you look a little bit, you can actually kind of see the outlines of my books up here. It doesn't show up so well here. But if you look at the notes online, you can see a little bit better. And out here's the window. This is looking out towards where the fountain is. That's a reflected image. So what I've done is 2 experiments. So I'm all about experiments, and let's see if they work. I took a camera. I took a picture of this in my office. And what I did is I put a linear polarizer in front of it. So I put a linear polarizer, took the picture. Now what we know is that the way that light bounces off this glass depends a lot. It comes off in a polarization-dependent way. Okay? So if I take that linear polarizer and I rotate it by 90 degrees, I get a slightly different image, which is here. It's the same thing. However, it looks like the same thing, but you'd actually get slightly different polarization states. And if you actually look carefully at the images, they're slightly different. So here's going to be the deal. I'm going to try to separate the image in the back from the image in the front, which is the reflection. I have 2 pictures here. The reflected picture, which is represented by this window, plus, you can't see it here, but there's my books up on the wall. That's image number 1 from the reflection. Image number 2 is what's underneath here, which is the Flaxman illustration of the Judgment of Paris. Okay? So I have 2 images superimposed. What I've done is given myself one more data set by doing the linear polarizer. And my objective is then just take these 2 images and separate them. Okay? Kind of cool, right? So you see how this might play out, right? I mean, this is something that, for instance, you can almost build it in directly into just, you pull up iPhoto on your Mac or any of these software things, and you say, separate image. And because what we're going to talk about is almost an algorithmic way of just pulling these things apart. Okay? All right, so that's going to be our objective for this week. So today, I'll talk more about the setup, the philosophy of what we're going to do. Wednesday, work out all the math that we got to do. Friday, apply it and clean up the image. Nice plan of attack? I think so. And you can imagine that you might do this actually not with pictures, but with real data. You have some data, and I want to just take the data and just separate out the data. So in that case, this is just philosophically. Keep in mind, this is not really an image processing thing. This is about data separation. The image just happens to be data. Okay, we're selling it this way, and it's really easy, at least from this data separation point of view, to see it as an image separation, because then you can say, oh, how well did I do? Oh, really pretty well, or not. Okay, and of course, just like the experiment in class last week, I think it might work. Matt will probably say, no, there's no way it's going to work. We'll see on Friday. We'll see on Friday. That's all I can say for now. I have no idea yet, because I haven't actually done it. I mean, I have the images, but I haven't done my algorithm to it yet. Okay, so let's talk about what we're going to do then with this. So is everybody okay with the premise of this thing? Okay, so let's try to set up this problem and learn how to think about this problem. It is no different than what we've been writing down here. 2 images need to be separated. When I read this at my camera, I have a linear combination of these 2 images. By taking that linear polarizer, shifting in 90 degrees, what I've got now is 2 independent measurements. I could have gone to another place, but that's actually for the image thing. You want to stay in the same place, take the picture, rotate the polarization, take a picture, extract out. I want to take away, I want to have that nice, beautiful Renoir in my frame. Okay? Actually, does Renoir picture people? He does, right? A little bit. But they got hats and dresses and stuff. My people are naked. You could tell. Okay, see? All right, anyway, Adam and Eve in the Garden of Eden. That's what I call that work. All right. Nobody's appreciating my art. You know what we're going to do? Field trip to the SAM. So if you guys can't appreciate good art, we'll go down there. Oh. British, exactly. I want to see whoever can touch the Rosetta Stone gets an A. Josh, you're strong. Start working because that glass is thick. You got to break through it and then touch that stone. But don't worry, it's all worth it. A few days in London jail, 4-0. It all pays off. I even pay airfare. Okay, so let's talk about separating this out, and let's talk about the SVD and how we want to apply the SVD to thinking about this problem. By the way, let me make one other comment. There are other ways to do independent component analysis. In fact, there are many ways to do this. There are a lot of statistical methods that have been developed, like statistical maximum likelihood ratios and estimates. These kind of things all play roles in doing independent component analysis. So I'm not saying that this is the only way. But what I am going to say is we're going to take this, and given what we've been doing with the SVD and the linear algebra, the sort of more applied math way of doing it, let's use that as the tool of choice in this thing. So it's going to be SVD and how it's going to impact our ICA. Okay. Everybody ready? I have two images. I have two measurements. So S is a vector which contains all my image information. X, these are my measurements that I have. X1 is with one polarization state. X2 is with the other state. Okay, that's the setup. And here's what I want to assume, and this is going to be very important for us. First, S1 and SS2 are not Gaussian distributed images. So it turns out, this is actually a good assumption, most natural images are not Gaussian distributed. Okay, we're going to make use of this fact. In fact, what we're going to make use of is higher order moments in a statistical distribution to get us what we want. That's typically what you do with independent component analysis. It's all about the higher moments. You use the higher moments to discriminate directions. Okay? 2, they are independent. What does it mean for two variables to be statistically independent? Well, if you remember from our definitions in class, from lecture, I think, number 2 of this class, here, the distribution, the joint distribution of the variables S1, S2 is just the product. It's separable of the two. Okay? Those are going to be the assumptions we make. All right. Now, what I'm going to highlight here is the cartoon of how this works. That's all I'm going to do. Class Wednesday, we're going to formalize this cartoon and put mathematics on it. Okay? But first thing you have to understand is the cartoon. If you don't understand the cartoon, the math isn't going to make any sense to you. Okay? So understand this cartoon. What is the cartoon going to be? Well, the cartoon, to understand this, is the fact that we know we can take any matrix A and do an SVD decomposition on this thing. So what does that mean? Well, it means take A and basically do that to it. What we've talked about is V and U are unitary, so they're just going to make rotations. Sigma is a stretching matrix. You stretch according to the principal components. Okay? So that's what this thing does. So think about it in the context of this. X is equal to AS, so X is equal to okay. So let's talk about what this does. I have two measurements. And let's start off with a simple assumption. Let's assume that S1 and S2 are somehow uniformly distributed variables. So let's start off with our original images. Sorry, S. At this point, they're unmixed. What I'm assuming is image 1 is given by some uniform distribution this way. Image 2 is uniform distributed this way, which they are basically not mixed. They're statistically independent. So I start off with a distribution. Okay, so in other words, I can live anywhere along in this plane. This is where my image plane is. What does the SVD do? First thing it does, rotates it, stretches, rotates. What does this look like? Take this thing, rotate it. Some amount. So when we go from here to here, that's under the action of V star. Stretch it. That's the action of C. Rotate it again. Okay, this is supposed to be the same size, but I'm running out of board space. So you all good with that? And then, so to get from here to here, you did the sigma. To get from here to here, you did U. This is what you actually measure, right? This is the ideal, if you actually had the images, this is what this matrix A would do to your image. This is not what you have. What you have is, you're starting up here. You're making this measurement right there. Okay? So here is the idea of independent component analysis. I want to take this mixed image that I have. In this framework, I've got to figure out how to separate them. The separation problem then comes down to simply this. How do I back this process out? In other words, how do I take this, rotate it down to that? How do I take this, stretch it back out to uniform distribution in each direction, and then how do I rotate it back to here? And this is going to be my approximate image, because when you think about doing this, you kind of go like, well, that's kind of, I'm undoing U, so it's U star. Remember, U star, it's a unitary matrix, so U star is its inverse. And then I want to that's what I want to do. I don't know the matrix A, though, by the way, right? I don't know the matrix A. That's the whole point. So normally I'd say, oh, take the matrix A, SVD. You do not know the matrix A. So philosophically, what you've got to think about in this process, say, I have a distribution like this. How do I find that? Well, first you've got to take your data. The first thing you've got to do is figure out, that's kind of like your sigma 1 and sigma 2 directions. So what you really want to do is when you look at this, this is the maximum variance along that direction. Next direction has a smaller variance. So the first thing you've got to do is pick out where that direction is. We'll take your original data, find out where the maximum variance is. Make that some angle. Okay, that's going to give you some angle here, let's say. And then make this orthogonal to it. So just make this. So you get to determine it directly from your data. You say, oh, well, I can kind of extract what that angle is of this stretched parallelogram that I've got, okay, for uniformly distributed data. So I know how to rotate it back to here. So you just rotate it back to here. Now, once you get the strengths of your variances, you can actually, how did we compress this? You remember, you compress this by having sigma 1, sigma 2 along the diagonals. So once you know your principal directions, strengths of your principal components, you know how to stretch it. Well, you can actually predict what the strengths of sigma 1 and sigma 2 from here are, and then you stretch it back. Once you stretch it back, then you say, okay, I'm still not done, because they're still mixed in this representation. The last thing you need to do is, now that you know this angle, you rotate it back to here. And once you rotate it back to here, and by the way, when you do these steps, you're going to have to use higher moments to figure out how to rotate it back. And we'll talk about that on Wednesday. But then you rotate it back to here, and what you've essentially done is you've backed out the SVD. You've backed out the U, the V, and the sigma. Now, once you have those, then the process is easy. You approximate each one of these pieces of the SVD, and then all you got to do now is say, oh, I want my original images. That is take my data, apply these matrices that I've built that are approximations to what should happen, get out the images. And that is the separation process. So we're going to talk about how to construct these UVDs, or U sigma and Vs, on Wednesday. On Friday, if all goes well, I'm going to take that raw data and either fail or come out a winner. One of the two. There's no middle ground, really. So, anyway, have a nice Monday. Nice, beautiful day. I think it's going to be beautiful for Monday and Tuesday, and then Wednesday it's going to start getting bad and rainy. Just thought I'd warn you right now.